So, um, we've seen a lot of, I think, interesting real world situations. I mean, I know for a fact that logistic regression is used, like the most basic form of it, and in a lot, probably most, useful real life settings. In fact, if you were to compare like logistic regression to its extensions, logistic regression I think is used probably like 80–90% of the time. That is, these extensions are important, but they actually cover sort of like a kind of fringe level um, of kind of situational examples. Nonetheless, it's not hard to imagine a situation where we might want to model something a little bit more nuanced, a little bit more granulated than just two values. That's kind of been the restriction that we've been sitting on, the restriction we've been sitting on so far. And so what we're going to talk about this week and next week is how we can get around that restriction. It turns out that we can fairly easily extend the logistic regression framework to categorical response variables, to categorical y variables that take more than two outcomes. And there's two such extensions. The first is referred to as the proportional odds model. The proportional odds model is used when we have an ordinal response variable. Remember, an ordinal response variable is that the categories of y have an inherent natural ordering to them. The second situation is when we have a nominal response variable. That is, the categories do not have a natural ordering to them. In this case, we would use something called the generalized logit model. That's what we're going to talk about next week. So we're going to talk about proportional odds model this week. We're going to talk about the generalized logit model next week. So the basic idea is this: for a categorical variable that takes k outcomes, what we essentially end up doing, and we've never done anything quite like this before, we essentially fit k-1 regression equations. So we've always just fit a single regression equation, both in 512 and in ordinary logistic regression. However, in the more general sense, if we have a y variable that has five outcomes, we need to fit 4 regression equations. Now, of course, if k equals 2, that's the situation of basic logistic regression, a dichotomous response variable. Then k-1 is 1, and so we're just fitting a single model, which is what we've done the last 3 weeks. Now notice that this basic idea is true for both proportional odds modeling, which we're talking about this week. It's also true for what we're going to talk about next week, the generalized logit model. Now, how we build or how we fit these k-1 regression models will differ depending on whether y is ordinal or nominal. But the idea that we have to fit k-1 of them is the same in both cases. So, proportional odds model, lets us work with ordinal variables. Maybe, for example, something like degree of injury. So maybe our y variable is degree of injury. It's not injured, yes or no, but it's degree of injury. And degree of injury has the possibility of no injury, but also possibilities of slight, moderate, and severe. So that's the type of situations that we're dealing with. It's also worth pointing out, right, when you're doing research on your own, when you're reading articles on the internet, when you're referencing other textbooks or references, that the proportional odds model is sometimes referred to as cumulative logit model. We'll see why in a second. Or ordinal logistic regression. We can already see why we call it ordinal logistic regression, because it's a situation where our y variable is ordinal. So let's actually explore this idea in its underlying mechanics in the context of an example. Let's look at an example where I think this is real life data. Been using it for so long, but I believe it was real life data, and it looked at a sample of car crashes and wanted to see if the outcome, and the outcome was death, severe injury, or no severe injury. So whether or not the outcome of the car crash depended upon whether or not the driver wore a seatbelt, yes or no, and whether the car was large or small. So here we have three outcomes, right? Not two. So we have a pi 1, a pi 2, and a pi 3. Pi 1 is the probability of death. Pi 2 is the probability of severe injury. Pi 3 is the probability of non-severe injury. Now we're building models. So these probabilities depend, all three of them potentially depend upon the type of car, large or small, and also depend upon, right, whether or not a seatbelt was used, yes or no. That's why we have that H and that I subscript. The H and the I subscript are just indicating, right, that these also depend on these extra variables. Now, let's go ahead and define these cumulative probabilities, right? Which is, of course, why it's sometimes called cumulative logit modeling. Because we don't deal with the probabilities, we deal with the cumulative probabilities. So instead of the actual probabilities pi, we're going to work with these cumulative probabilities theta. So theta 1 is going to actually be the same as pi 1, but theta 2 is going to be pi 1 plus pi 2. Now notice we technically don't need a theta 3, right? Because theta 3 would be what? Theta 3 would be pi 1 plus pi 2 plus pi 3, but that would just be 1, agreed? Now, if we had four outcomes, then we would have a theta 1, a theta 2. Theta 3 would be pi 1 plus pi 2 plus pi 3, and then theta 4 would be 1. But essentially, with three outcomes, we have two thetas. For k outcomes, we would have exactly k minus 1 thetas. Once we have our thetas, we then define these cumulative logit functions. We do the logit for theta 1, we do the logit for theta 2, and of course there's no need to do a logit for theta 3, because that would just be like a logit of 1. And of course the logit is still defined in the following way. It's the logit is, you take whatever the input is, and you do the log of that over 1 minus that. So in this case, that's going to be the log of pi 1 over pi 2 plus pi 3. Conceptually, this is the log odds of death, right? That's outcome 1 to injury, right? Because, right, outcome 2 is severe injury, and outcome 3 is no severe injury, so a mild injury. So it's death to some type of injury, either severe or mild. And then logit of theta 2 is, well, theta 2 is pi 1 plus pi 2, and then the denominator is 1 minus that. So 1 minus that's just pi 3. So this is the log odds of death or severe injury to no severe injury. All right, and of course now we see, right, these are our two equations, right? We have our two sort of y variables. Does that make sense? I mean, kind of big picture, the idea is what? That at the end of the day, we often are interested in estimating probabilities, right? And so if we have an outcome, or if we have a variable with three outcomes, If we can estimate 2 of those 3 probabilities, then we know the third, right? Based on the fact that all probabilities add up to 1. That's kind of the idea behind why we have to fit more than one equation. If there's 3 outcomes, we need 2 equations, because those 2 equations, we'll see, will ultimately let us estimate 2 probabilities. Once we have those 2 probabilities, we could use those coupled with the fact that all probabilities add up to 1 to solve for the third probability. And this is how we set these equations up. So we're going to have one of our equations, our left-hand side is going to be the logit theta 1, and our second equation, the left-hand side, is going to be logit theta 2. Now, more generally, for some response variable with k categories and p explanatory variables, we have to fit k-1 equations of the following form, right? So there's that theta. That theta is essentially, right, all the probabilities less than or equal to it. So, right, theta 4 would be all the probabilities less than or equal to 4. So it would be pi 1 plus pi 2 plus pi 3 plus pi 4. So that logit of the cumulative probabilities up to outcome k are equal to some y-intercept. Here it's convention to use alphas rather than beta naughts. And then some slopes, right? So we have p variables. So, right, there's p slopes. But notice our slopes have 2 subscripts because, right, our slopes can potentially differ based on variables, but also based on our equations, right? So the first variable, x1, could potentially have different slopes for every one of its different logit equations. However, we simplify this often by applying what's referred to as the proportional odds assumption. And the proportional odds assumption is this, that when we have an ordinal response variable, so we would only apply this in situations where y, right, is an ordinal response variable, that beta ik equals beta I for all k. So it's basically, what is that saying? It's saying that, right, our models simplify to the following form. That logit of theta k is alpha k. So we're allowing the y-intercepts to vary from equation to equation to equation. In fact, the y-intercepts are the only differences between our equations. But the equations are all the same in terms of the slopes for the x variables. That's the proportional odds assumption. That is, a 1-unit change in x of I has the same change in log odds for any of our k-1 models. Now, we can reverse, so once we fit these models, or had SAS fit these models, we can reverse these models using the formulas from before. It's just when we apply the formulas from before, what they're solving is they're solving not the actual probabilities, but the cumulative probabilities. So, right, we can do that e to the delta over 1 plus e to the delta, where that delta is just our model equation. And if we apply that to the first equation, that actually will get us pi 1. But if we apply it to the second equation, that's going to get us pi 1 plus pi 2. And if we apply it to the third equation, that's going to give us pi 1 plus pi 2 plus pi 3. That is, the formula that we've used in the past solves for cumulative probabilities, not the individual probabilities. But that's not a big deal, right? Because if we get the cumulative probabilities, we can use those to determine the individual probabilities. So it should be evident to us. I already said that if k is 3, we have 3 outcomes, like in our car crash example. So pi 1 will just be theta 1. Now theta 2, we said, is technically pi 1 plus pi 2. So if I want pi 2, that's just theta 2 minus theta 1. And then it should also be evident that pi 3 is 1 minus theta 2. Again, this should, if we sit and reflect upon it, make sense to us. If it doesn't, that's a big deal. That's an egregious conceptual gap. It's understandable that it's there, but we do not want it to be there. So you need to reach out to me so we can remedy it. All right, let's go back to our seatbelt example. So we have this x variable, 1 if it's large, 0 if it's, I actually think the data set calls it compact instead of small. And then x2 is 1 if it's a seatbelt, 0 if they're not a seatbelt. So, right, theta 1 is going to be the probability of death, that's outcome 1. Theta 2 is going to be the probability of death or severe injury, right? That's the probability of outcomes 1 outcomes 1 or 2. So this is the two equations that we're fitting. Notice what? So what do we have? We have 4 parameters that need to be estimated, right? Alpha 1 and alpha 2, and then beta 1 and beta 2. The proportional odds assumption is assuming that the beta slopes are the same in each equation. Now, this does not have to be true. There are a whole bunch of real life phenomena that do not follow the proportional odds assumption. And so in those cases, a proportional odds assumption would be inappropriate. But if we're applying that assumption, this is what our model equations would look like. We'll talk in a little bit about how to test for the appropriateness of this assumption. So yeah, under the proportional odds assumption, instead of 6 parameters, we need to only fit 4. Now we have those 2 logit equations. They differ in terms of what's on the left-hand side of those equations. Now, in terms of the right-hand side of the equation, we have 2 explanatory options, or explanatory variables, both of which have 2 options. So there's 4 covariate patterns. Large car seatbelt, large car no seatbelt, compact car seatbelt, compact car no seatbelt. So 4 covariate patterns, but 2 equations. So if we were to write everything out, that's a total of 8 equations. I'll leave it to you if you want to write all of those out. I give us a little bit of a taste of it, I think, in an upcoming slide. Oh, all right, here's that upcoming slide. So for example, right, if you wanted to look at the odds of death or severe injury, well, so the log odds of death or severe injury to no severe injury while driving a large car while wearing a seatbelt would be alpha 2 plus beta 1 plus beta 2. So that's actually one of those 8 equations. If we wanted the odds of that instead of the log odds, we just exponentiate. We can also get odds ratios by exponentiating parameter estimates. So, for example, beta 1 is the coefficient associated with car size. So if we exponentiate beta 1, or right, in terms of what SAS gives us, beta 1 hat, that'll give us the odds ratio associated with large cars. Now notice, because of the proportional odds assumption, we can interpret this e to the beta 1 or e to the beta 1 hat as the odds of death versus not dying due to large cars, or the odds of death or severe injury to no severe injury due to driving a large car. We're part of the proportional odds assumption is saying that both of those odds ratios are going to be the same. That's a byproduct of the proportional odds assumption. So, two side considerations, and then we'll kind of wrap up with our example. One is, how do we test whether or not the proportional odds assumption is in fact appropriate? And then what about goodness of fit tests? So we said the proportional odds model assumes, right, and this assumption may or may not accurately reflect the underlying reality, but the proportional odds model assumes that the slope coefficient for each variable is the same in each of our k-1 logit equations. And of course that may or may not be true, so we need to test it. How? How do we test it? Well, we use the test for proportional odds. If we have p slope coefficients, so p variables, then we're essentially doing p of the following composite tests. So, right, the null hypothesis is that, right, say for beta 1, the beta 1 coefficient for all k-1 equations is the same, and the beta 2 coefficient for all k equations is the same, and we do this for, right, all p variables. More simply, the null hypothesis is that the proportional odds model is appropriate. That each variable has the same slope in all of our k-1 equations. So we hope to fail to reject. Failing to reject means that the proportional odds assumption is appropriate. Should we instead reject, that means that we need to fall back upon, we need to use another type of model, for example, the generalized logit model that we're going to talk about next week. Now, SAS does this test for proportional odds automatically by default, and it turns out that for a sufficiently large sample size, the test statistic follows a approximately chi-squared distribution. With p, that's the number of variables, times capital K, that's the total number of outcomes that our y variable has, minus 2 degrees of freedom. In terms of sufficiently large, we want to aim for at least 5 observations at each level of main effect. Keep in mind, though, that samples that are too small, we can actually, when samples are too small, we sort of know what direction to expect the bias to be. It turns out when our sample's too small, our test statistic is too large, which implies, right, and this implication should make sense to us if we reflect upon it, it implies that for small samples, we could be comfortable in justifying the proportional odds model. If that's what our test tells us to do. And in terms of goodness of fits, assuming we have the large enough sample size, we can use the Pearson or deviance. We could also use a likelihood ratio test where we compare our model of interest to a saturated model. And then we could also do, I believe, Hosmer and Limshow tests. Note that SAS does proportional odds modeling by default whenever it notices that y has more than 2 values. So that is definitely not appropriate if y is nominal. So we need to be aware of what SAS is doing. right? We cannot use this code if it's a nominal variable. We can only use this code if it's ordinal. Also remember, right, if these do have ordered categories, we have to make sure that SAS is ordering them correctly. By default, it's going to order them alphabetically. We can override these defaults with, just like before, just like back in our table portion of this class, with an order equals statement. And so here's our proc logistic code, slowly kind of building up in terms of its complexities. Notice that order equals option, so that's going to order the outcomes of the y variable by the order they appear in our data set rather than the SAS alphabetical default. So our class variable is, so we're going to use the class statement. And we're going to use reference parameterization. We're going to model death, another nice morbid example to add to our collection. We're going to model death as a function of seatbelt type of car and seatbelt practices. And then to get the goodness of fit test, we do that scale equals none aggregate. To be able to get estimated probabilities, we need to output them into an output data set. So here's our output. Notice at the very, very bottom is our test for the proportional odds assumption. The p-value is quite large, 0.7074, well above 0.05, which means that the proportional odds assumption is reasonable. So we're good, assuming proportional odds. Our goodness of fit test statistics on the very top, they're well over 0.05, indicating that our model fits the data well. Our global tests are all highly significant, indicating that at least one of our variables is significant, indicating we should dig deeper. Digging deeper, right, we see that both type of car and seatbelt are very significant. So each of those is important in our model. And then we see our model equation. Notice our model equation, SAS fits two y-intercepts, one for the death equation, one for the severe injury equation, but both of those equations are going to use the same coefficient for type of car and for type of seatbelt. Notice the negative coefficients indicate what? The negative coefficients indicate that large cars have a lower incidence of severe injury, and the negative coefficient for seatbelt indicates that those wearing seatbelts have a lower, because it's negative, incidence of injury. There's our odds ratios, verifying what I just said about them being lower. And of course, the odds ratio quantifies specifically how much lower. Here is the outputted probabilities. A lot of redundancy there. Now keep in mind, as I've already specified, these are cumulative probabilities. I'm going to, in a future slide, solve for the individual probabilities, and when doing so, you may want to reference back to this slide, which is where I'll be getting the actual numbers from. So walking kind of through our steps, first thing is our response variable ordered correctly. I forgot to point that out to us when I looked at the output, but if you go back and look at the output, which you should, you will see that they were ordered correctly. We saw that the proportional odds model, our test of proportional odds, indicated that it was a reasonable assumption. Our goodness of fit tests indicated an adequate fit. Our overall tests were highly significant. And both variables were significant at the 0.05 level. So let's look at odds ratios and their interpretations. So the odds ratio for type of car, was reported by SAS as 0.475. So we would interpret that as the odds of death to no death, or the odds of death to some type of injury, severe or not severe, for large cars is about half, so 0.475 times that of compact cars. All other variables held constant. So assuming we're comparing people who both are wearing seatbelts or people who are both not wearing seatbelts. Now, as a consequence of the proportional odds assumption, and if the proportional odds assumption was not satisfied, we cannot make the second claim. But because our test indicated that it was a reasonable assumption, we could also say the odds of death and severe injury to no injury for large cars is about half that of compact cars. Again, all other variables held constant. If we wanted to interpret the odds ratio for seatbelts, that's about 0.337, or about a third. So we would say the odds of death to injury, or the odds of death to no death for those wearing seatbelts, is about a third. Those who do not wear seatbelts, all other variables held constant. Again, a consequence of the proportional odds assumption, and only true if that assumption is true. We could also say the odds of death or severe injury to no injury for those wearing seatbelts is about a third of those who do not wear seatbelts. Again, all other variables held constant. Now, the last thing for us to look at is estimated probabilities. We have 12 such probabilities, right? We have 3 probabilities that we're interested in: death, severe injury, no severe injury. And we have 4 covariate patterns. So 3 times 4, right? 12 probabilities. In terms of the output, we focus on type, belt, and that level and prob variables. The other columns are not relevant. Keep in mind, as we already pointed out, that the probabilities that SAS is reporting are cumulative probabilities, not the individual probabilities that we would most likely be interested in. So, you should be able to get and verify these numbers from the output on the previous slide. If you cannot, then reach out to me. I think I do like 6 of the 12. So first I focus on seatbelt wearers in compact cars. What are the 3 outcomes? Death, severe injury, no injury. The probability of death we can get directly from the output. Probability of death, if you're wearing your seatbelt and driving a compact car, that's 0.14514. Now, if you look at seatbelt wearers, compact cars, in the situation where we have a severe injury, you'll see that SAS reports the value 0.34649. This is a cumulative probability. So if we want, that's the probability of a severe injury or death. If we instead just want the probability of, if instead we want just the probability of severe injury, we do that 0.34 minus the 0.14, so we get about 0.20. And then finally, the probability of no injury is 1 minus the 0.34, right? It's 1 minus the probability of a severe injury or a death. So if it's not severe injury or death, the only outcome left over is no injury. So we get 0.65351. And then here's one last example. If you're focusing on non-seatbelt wearers in compact cars, same logic. We can get the probability of death directly as 33%. The probability of a severe injury, we look up the 61118 and then just subtract from that the 33%. And then the probability of no injury is 1 minus the 61%. So looks like the probabilities are about a third, a third, a third. All right. Any questions? Good. Then what I want you to do yourselves is, fill in the probabilities. There's still 6 remaining probabilities. I think it would be what? It would be seatbelt wearers in large cars and non-seatbelt wearers in large cars. So make sure you do those other probabilities. If you're not sure about those other probabilities, then try to solve them and shoot me an email and say, hey, I think this is what they should be. Do you mind letting me know if I'm correct? And of course, I would be happy to let you know that in fact you are. All right, that wraps up this week's lecture. I'll see you next week when we talk about the generalized logit model.